morning everybody. Today we are going to see what is chemical bond. Chemical bonds refer to a kind of attraction between atoms. It is very important principle of chemistry. So, understanding about the bonding is very important to explain any property of a molecule. For example, take a carbon dioxide. Carbon dioxide is a greenhouse gas, one of the greenhouse gases. It is present in the atmosphere. It is not allowing the heat from the surface of the earth to dissipate out. As a result, the temperature on the earth surface is increased. But if you consider that it is not the only carbon dioxide present in the atmosphere, there are other gases, for example, nitrogen and O2 are present in large quantities, but they are not called as greenhouse gases. But the if you look at the amount of carbon dioxide present in the atmosphere is 0.04% only, but it contributes to the global warming. What is the reason? It is something to do with the nature of the bonding present in carbon dioxide. This is the carbon dioxide structure. Okay, it is a linear molecule, and the central atom is a carbon connected and surrounded by two oxygen atoms. So, it is because of its chemical bonding, it contributes to the global warming. So, you know that heat energy is related to the infrared radiations. So, carbon dioxide has a bonding pattern in such a way that it absorbs light in the infrared region, which is related to the heat. That is the reason carbon dioxide contributes to the global warming. So, you can from this, if you look at that nature of the bonding in N2 or O2, they are not contributing. It is because of the nature of the bonding in them. So, it becomes more important to understand what is the nature of the bonding in each molecules. How to understand the bonding? So, if you look at the elements combine to form a molecules. Molecules are lower energy compared to the elements. So, after bond formation, energy of the molecule is lower compared to the elements. Why? These are the things we have to have in mind to understand the bonding. So, to explain the bonding between atoms, let us consider the model, so-called the model called electrostatic potential energy model. Electrostatic potential energy model. Electrostatic potential energy model. Electrostatic potential energy model. So, using this electrostatic potential energy concept, one can explain the bonding between atoms. So, under this concept, electrostatic energy is given by is directly proportional to charge, given by proportional to the product of the charge Q1 and Q2, and then inversely proportional to the distance between the charges. So, electrostatic energy is once again directly proportional to the product of the charges and inversely proportional to the distance between them. So, if you have a charge of negative sign, and if you have a particles and its charge is positive, when they approach each other, because one particle is positive, another particle is negative, they are attracted to each other. When they approach each other, the energy is decreasing. Okay. So, because the charge on one particle is negative and the charge on the another particle is positive, the product of positive negative is negative. So, energy becomes negative, energy becomes negative as they approach. Okay, as they approach, that energy will become further negative when the distance between the particles decreases. So, energy is ultimately decreases when two particles are oppositely charged approach each other. EL becomes negative as the particles approach each other. So, if we have for example, we take a cation, say as A plus is approaching B plus, B minus. When they approach each other, there is a attraction between them, energy is decreased as the distance between these particles decreases. So, and then it reaches a minimum energy where they are stable, okay, where it attains the maximum minimum energy, which can be represented by a diagram like this. This is a potential energy, electrostatic potential energy. In kilojoules per mole, and this is the distance between the nuclei, distance between the particles. Now, if you say this is a energy is 0, and then the particles are away at one time. So, there are two particles, here is the A particle which is its charge is positive, and here is the B particle, its charge is negative, and they approach each other. Okay. So, the energy of the system decreases. Okay. When they approach each other, energy decreases. That can be represented by this diagram, as it is like that. So, they approach still more closer and closer to each other, the energy decreases. That is why I am putting the diagram, the energy is 0, above is positive, below is a negative. So, energy becomes negative as then it reaches a minimum, and then after that it increases. Okay. So, as I explained before, okay, it is a product of charges. Directly, energy is directly proportional to the product of charges and inversely proportional to the distance. So, as particles approach each other, the energy of the system decreases and reaches a minimum here. Okay. After that, energy increases again. What is the reason? That is what you have to include. If you take a particles, okay, or ions, it has electrons and nucleus. So, how much they can approach each other? This much or this much? No, they cannot approach each other beyond certain distance. Okay. So, what will happen if they approach too closer? There is a repulsion between particles, because each particle has electrons as well as protons. The electrons present on one particle repels the electron present on the other particle. Similarly, the proton on one particle is repels, okay, the proton of the another particle. So, as a result, there is a repulsion between like charges, okay, that will lead to a increase in energy. That is the reason. So, this is a particular distance, okay, energy is minimum. Okay, this is a energy at this distance, okay, and this is a distance at which this is a energy. Okay, this is a distance at which this is a energy. So, So, at this point the repulsive and attractive forces are balanced. Okay. If you go beyond this or less than that distance, then the forces are not balanced. Okay. So, it is that point attractive and the repulsive forces are in balance, okay, and the energy is minimum. So, that distance is okay, is characteristic of each atom. For example, so this concept, this model can be used to explain the ionic bond. As I said before, you take a particle of A plus and B minus, okay, because they are oppositely charged particles, they approach each other because they are attracted to each other, and then they form a ionic bond, they form ionic bonds, ionic bond. So, you can explain if the particle, okay, formation of ionic bond by this type of electrostatic potential energy model. Okay. What about bonding between two neutral atoms? For example, hydrogen atom, hydrogen A, for example, say hydrogen atom A, hydrogen atom B, okay, and then they form hydrogen molecule, a hydrogen molecule is formed. How do you explain that? The bonding between two hydrogen atoms which are neutral by this model. One can also explain the bonding between the two neutral hydrogen atoms by this model. How? Because each atom has negatively charged electrons as well as positively charged protons. So, it is possible for the atoms to attract each other. Okay. So, then the same way one can explain the bonding between two hydrogen atoms. For example, here the two hydrogen atom A and A are far apart, they are well separated and there is no attraction between the two particles. As a result, potential energy for that system is 0. So, that at this distance, okay, so this potential energy is 0. So, energy is 0, but as the distance decreases between the two neutral hydrogen atoms, the energy decreases like this. Okay. So, this is a distance. So, the energy, the distance, this is a distance this way, the energy is this way. So, energy decreases when these two particles approach each other and then reaches the minimum, okay, the optimum distance between them, at which the minimum energy is, this is the minimum energy is obtained. Okay. After that distance, any distance after any decrease in distance will lead to a increase in energy. Okay. That is what happening. So, two hydrogen atoms combine to form a molecule can also be explained by this electrostatic model. This is very general way of treating chemical bonding, although there are several, okay, there are very good theories exist there, we will see that later on, but one can look at the bonding by this model as well. It gives some general idea about chemical bonding. So, as you can see here, the energy is decreased at this distance. Now, what is the distance for two hydrogen atom which leads to a hydrogen a bond between two hydrogen atoms? The distance is, the distance in this place, it is a HA and HB. Okay. So, this distance corresponds to 74 picometer. So, any distance lower than this, for example, 73 picometer will be in higher energy, okay, compared to 74. So, that is the distance between the two hydrogen atoms. So, that distance refers to so called bond length. Okay. The distance is 74 picometer. So, 74 picometer is called bond length. And the energy at that distance is electrostatic energy, electrostatic potential energy is minus 432 kilojoules per mole. So, that much energy is released when two hydrogen atoms combine to form a one molecule of hydrogen gas. Okay. So, that much energy is released when. So, you can see from this explanation that the energy of the hydrogen molecule is lower in energy compared to its elemental form, hydrogen atoms. So, that is the reason bonded molecules are lower energy compared to the elements from which the molecule is formed, So, this is the energy. So, that means as you can see here, so this is a distance at which this is energy. Now, suppose if you want to cleave this two hydrogen atom apart, then one has to give that much amount of energy, that is 432 kilojoules per mole energy to be given to a hydrogen molecule to break the two hydrogen atoms apart. So, that means 432 kilojoules per mole of energy is to be given to cleave the H2 molecule. Then you will have the elemental hydrogen atoms. So, you can tell that 432 kilojoules per mole is the energy of the bond between the two hydrogen atoms. So, it is the 432 kilojoules per mole is the bond energy of the bond in hydrogen molecule, that is a bond energy. So, from this it becomes clear what is bond energy, what is a bond length. So, you have one hydrogen atom, you have another hydrogen atom, let us say this is HA, let us say this is HB, this is a nucleus, this is nucleus. The distance between the two centers of the sphere, two hydrogen atom, is 74 picometer. So, that distance refers to a bond called covalent bond. This bond is called covalent bond. So, as you can see here, what is covalent bond? Covalent bond is formed between two hydrogen atoms. That is a one type of bond in chemistry. There are several type of bonds. Another one is the ionic bond, covalent bond. Another one is the ionic. Another one is the metallic bonds. There are other bonds, hydrogen bonding, there are weak forces. These are the three major types of bonds in chemistry, using which one can explain or one can understand the property of the molecules. So, what is covalent bond? Covalent bond is formed by between two atoms, for example, in hydrogen molecule. Now, we have some idea about what is covalent bond. We will see about covalent bond more later on. Now, let us see briefly about what is ionic bond. Ionic bond is formed between two ions, which can also be understood by potential energy diagram. And then when you consider ionic bond, it is basically formed between metal and non-metals. Metals and non-metals. Non-metals on the right side of the periodic table, metals primarily electropositive metals on the left side of the periodic table. So, when they combine, so they form a ionic bond. Covalent bond is formed primarily by non-metals as well as metalloids. Ionic bonds are formed between metal and non-metals. Another bond is called metallic bond. Metallic bonds are formed by metal itself. So, if you consider what is metallic bond? If you consider metals, for example, sodium metal. So, I am drawing the sodium metal as a circle like that, and then there is another sodium metal, and then another sodium metal, another sodium metal, another sodium metal, and then another sodium metal. It has a nucleus there everywhere. Each atom circle, each atom has a nucleus. Now, there is these metal atoms exist together because there is a bonding between them, otherwise they cannot exist together. What is the nature of the bonding in them? That nature of the bonding is called metallic bond. Metallic bonds also involves sharing of electrons. What we saw just now is the covalent bond, in which electrons between two hydrogen atoms is shared, which is very important concept. Electrons are shared to form a bond. That is what called covalent bond. Similarly, the same thing happens in metallic bond formation as well. Unlike covalent bonds, in covalent bonds we have seen a pair of electron is shared between a pair of atoms, but in metallic bonds electrons are shared not only between two atoms, electrons are shared among several atoms in metals. So, metals, which are what I drawn here, is only a two-dimensional figure. Metals are arranged in a three-dimensional way. So, here again there is a sharing of electrons among the atom. It is not sharing between any two metal atoms, sharing of electrons among several atoms. Such shared electrons are not located at between two atoms, and they are actually moving around all over the metals. So, that creates a sea of electrons in which the nuclei present. Because of movement of these shared electrons among several atoms, metals have a characteristic properties such as conductivity. It is a very good conductor of heat and electricity. So, that is a difference, major difference between the covalent bond and ionic bond is that in terms of sharing of electron between two atoms or several atoms. In covalent bond, the shared electron is located between two atoms, but in metallic bonds the shared electrons are moving around all over the atoms. As a result, there is a sea of electrons. So, electrons are free to move, they are delocalized, so called delocalized. Electrons are delocalized. So, electrons are delocalized in metals, they are free to move, that means freely moving. So, as a result, they are very good conductor of electricity and heat, but in covalent bond basically is a sharing of pair of electron. Between two atoms. In metallic bonds, shared electrons are delocalized. So, that is the reason they are very good conductor of heat and electricity. Now, let us move to a different concept, so called Lewis dot structures. Lewis structures. G.N. Lewis is a chemist, a great American chemist, proposed a rule called Octet Rule. He is the only one, he is the first person showed that bonds are formed by sharing of electrons. Okay. He wanted, what he proposed is that to form a bond, 2 electrons are needed. So, by sharing 2 electrons between 2 atoms, a bond is formed. That concept is a revolutionary concept first proposed by Lewis before quantum mechanics orbital concept arrived. So, that was a great idea proposed by G.N. Lewis, and he proposed, what he did is that he looked at several molecules, several stable molecules of the second row elements of in the periodic table. For example, he looked at several molecules, stable molecule, for example, water, and then ammonia. These molecules are very stable, and then you can take O2. These are the molecules formed by the second row elements, main group elements, and these molecules are very stable. And then he noticed these molecules, the number of electrons around each atom is 8. Okay. Second row elements means energy level is 2, n equal to second row. For second row, n equal to 2, and they have s and p orbitals. When these two orbitals, s orbital can accommodate 2 electrons, p orbital can accommodate 6 electrons. In total, there are 8 electrons. So, then once these two cells are filled up, then you will end up with closed shell configuration, which is well known for noble gas. Closed shell noble gas, for noble gases, or they are called inert gases. So, they are inert because they are not chemically reactive, although there are several compounds nowadays, but its inertness initially attributed to the closed shell configuration, its closed shell configuration. Similarly, when he looked at the number of electrons around each atom in this type of molecules, and he found that there are 8 electrons are shared among the between the atoms. If you take for example, O in water molecule, number of electron around this oxygen atom is 8. How? There is a bond, a single bond. This is called single bond. A single bond means 2 electrons. Double bond means 4 electrons are shared between atoms. A single bond means single bond means 2 electrons shared between two atoms. Double bond means 4 electrons. So, when he looked at the number of electrons around each atom and he found that it is 8. So, there is a single bond between oxygen atom and hydrogen atom. So, that means there is a 2 electrons. There are 2 electrons in there, and in addition these two lone pairs, these two are called lone pairs. Okay. Unshared pair of electron on atom is called lone pair. Okay. There are 2 lone pairs on this oxygen atom. What is lone pair? Unshared pair of electrons is called lone pairs, which is present on this oxygen atom. And so, and there is another single bond between this oxygen atom and hydrogen atom. So, in total there are 8 electrons, 2 electron here, 2 electron here, 4 plus 2 electron here, 6 plus 2, 8. So, total it has 8 electrons. Similarly, if you look at the number of electron around this nitrogen atom is 8, because there is a 2 electron here, there is a 2 electron here, there is a 2 electron. So, there is a lone pair. So, in total 8. Similarly, you can count the number of electron around each oxygen atom here as well. So, that is the reason he proposed a rule called Octet Rule. Octet means 8. So, if you have a molecule and it is stable, and then the atom, okay, each atom in it should have 8 electrons. So, then that molecule is stable. Then he come up with a rule called Octet Rule. According to this Octet Rule, each atom in a molecule should share 8 electrons with its neighboring atoms. So, that is a rule proposed by the Octet Rule, and in addition he said also that a pair of electron is needed to form a bond. Sharing of electron concept is the original concept of G. N. Lewis, from which other theories developed. For example, valence bond theory is developed from the original idea of sharing of electrons, pair of electron, sharing of electron between 2 atoms. Now, there is a symbol called Lewis symbol. What is that? It represents now how many valence electron present on a particular atom. For example, if you take a boron, okay, its Lewis symbol is like this, like this, like this. This is a Lewis symbol of boron. So, boron belongs to a group, okay, group 3. So, its number of valence electron is 3. Boron has 3 valence electrons, which can be shown like this. So, this is called Lewis symbol. So, that means, for example, carbon has 4 valence electron. So, which can be represented by this way. So, these are called Lewis symbols, which represents how many unpaired electrons present on them, how many unpaired electrons present on that. So, using Lewis symbol, we can draw so called Lewis structures. To draw a Lewis structures, it is important to know how to draw a Lewis structures, because whenever you are writing organic reaction mechanism, for example, you need to know how to draw a Lewis dot structure. So, for that purpose, it is important to know how to draw a Lewis dot structure. There are 5-6 steps one has to follow to draw a Lewis dot structure, drawing Lewis structures. To draw a Lewis structure, you must first count the number of valence electrons of each atom in a molecule. First step, step 1, determine the number of valence electrons. That means you have to count the valence electron for each element. For example, water H2O. Okay. The valence electron for hydrogen is 1. So, for this one it is a 2 into hydrogen plus O. The valence electron for hydrogen is 1, 2 into 1 plus the valence electron of oxygen is 6. So, in total there are 8 electrons. So, like that one has to first find out the total number of, determine the number of valence electron, total number of valence electron available for bonding. We are concerned about valence bond, okay, so called valence electron, because bonds are formed using only valence electrons. Core electrons are not involved in bonding. So, here for writing Lewis structures, we are concerned about number of valence electrons, that you can find out from the group itself. Third group elements means valence electron is 3, fourth group elements means the valence electron is 4, fifth group elements means nitrogen valence electron is 5. Similarly, sixth group element is the oxygen, its valence electron is 6. For fluoride it is 7, for neon it is 8. So, like that you can find out the valence electron. The first step is to determine the how many number of valence electron present to draw a structure. The second step is the step 2. Find the central atom. Find the central atom. What is a central atom? If you take a molecule, there will be a atom surrounded by other atom. So, the middle atom is called central atom. That one has to determine. How to determine the central atom? That is a question. That usually the central atom is usually less electronegative element, or the element has the highest, greatest bonding capacity. Central elements, central atom is the one has the greatest bonding capacity. What is bonding capacity? Bonding capacity refers to the number of unpaired electron present on an atom. For example, if you take a boron, okay, boron has 3 unpaired electrons, 1, 2, 3. Carbon, there are 4 unpaired. Paired, unpaired. Paired means dot, okay. Unpaired means they are not paired. So, there are 4 unpaired electrons for carbon. So, carbon has the highest. So, bonding capacity refers to the number of unpaired electron present on the atom. Higher the number of unpaired electron, higher the bonding capacity, like that. So, compared to boron, carbon has the highest bonding capacity. So, or you can also choose the central atom based on electronegativity. The less electronegativity negative element is usually the central atom. That way also you can choose. So, now we know that the number of valence electrons, and we know what is a central atom. Then the third step is the draw a approximate structure. So, after determining the what is the central atom, one has to draw a structure, approximate structure. For example, water molecule itself, H2O, you have a central atom oxygen, okay. Oxygen has the highest bonding capacity, and then you have to draw a bond between oxygen and hydrogen. So, for example, another example is chloroform, CHCl3. The central atom is the carbon. Okay. Now, after determining the what is the central atom, you have to arrange the remaining atom, okay, around this central atom. For chloroform CHCl3, carbon is the central atom. You put the hydrogen here, and then, okay, 3 chlorine atoms around that, and then you draw a single bond between atoms like that, because there must be a single bond, there must be at least one bond must be present between each pair of atoms. So, there must be a single bond between the a pair of atoms. A single bond refer to 2 electrons. Then that means the third step is subtract, okay, subtract. For forming single bonds from the total valence electrons. Okay. And then you have to step 4. In step 4, you have to distribute the remaining electrons after subtracting the electrons which are consumed for forming a single bond, okay, should be distributed, okay, at the terminal atoms. Distribute remaining valence electrons as pairs around each terminal atoms, so that each atom attains octet of electrons, except hydrogen. You cannot put a pair of electron, okay, more than 2 electrons around hydrogen atom. Hydrogen has only one orbital called 1s orbital, and it can accommodate only 2 electrons. So for hydrogen, that is the first row elements, it requires only a duet of electrons. Hydrogen requires duet or duplet of electrons. 2 electrons are enough around hydrogen atom. So the fourth step, we have to distribute the remaining electrons around each terminal atom, so that each atom attains 8 electrons. Now step 5, it will become clear when I discuss about examples, but if you do all this in a stepwise fashion, and there will be no error. After distributing the valence electrons around each atom, you have to do match the number of electrons, match the number of electrons distributed to the number of valence electron counted in step 1. It should match with that, because number of you calculated first number of valence electron, and that those electrons were distributed now. After distribution, the number of electrons should be the same as what is counted. Okay. You have distributed the number of electrons in such a way that each atom has 8 electrons. Suppose if there are more electrons present, that more electron, okay, the leftover electrons should be added or should be given to the central atom. And then in step 6, complete the octet. For the fifth, okay, in the 6th step, you have to make sure that the central atom is having 8 electrons. If it has 8 electrons, then the structure is done. Let us see, okay, and a few examples from which it becomes very clear. So, let me show you one more time how to draw a Lewis dot structure. First step is that find out the number of valence electrons. Okay. For a given molecule, you know that what are the atoms present. So, from the group number, you can find out the number of valence electrons. So, add them together, then you will have a total number of valence electron. That is the first step, determining the total number of valence electron. And then you have to choose what is the central atom. After choosing the central atom, you arrange the remaining atom around the central atom. Okay, and then draw a single bond between them, because all atoms are held together by at least one single bond. So, you draw a minimum bond, that is one single bond between each atom. So, for forming one bond, 2 electrons are consumed. So, you count the number of single bonds drawn, that number of electrons should be subtracted from the total number of valence electron. Then whatever electrons remaining should be added to the terminal atoms. The terminal atoms means the atom located outside the central atom. You have to add electron as pairs in such a way that each terminal atom attains 8 electrons. And then you have to look at the number of electrons added. The number of electrons added should match with the number of electrons originally counted. It should be the same. It should not be less or more than that. After you make sure that each terminal atoms attains 8 electrons. If you have excess of electron, that excess of electron can be added to the central atom. And then you have to make sure that the central atom has octet of electrons. If does not have, then there is a mechanism of doing that. You have to bring a pair of electron or lone pair of electron to the central atom and convert it into a double bond, and then you count the number of electrons, it will be 8 electrons. These things will become clear as we see more examples. Let us see an example how to draw a Lewis structures for chloroform CHCl3. The first step is the valence electron. How to do that? There are carbon, there is a hydrogen, okay, plus there are 3 chlorine atom. Valence electron for carbon is 4, plus valence electron for hydrogen is 1, plus 3 into valence electron for chlorine is 7. So, that is equal to, okay, that is equal to 21, 22, 26. 26 valence electrons are there in chloroform. Now you have to draw the, you have to find out the central atom. That central atom is the carbon, because carbon has 4 lone pair, 4 unshared, okay, unpaired electrons. So its bonding capacity is higher compared to other atoms here. So you have to arrange the remaining atom, okay, that is hydrogen and chlorine around the central atom. You draw a hydrogen atom here and chlorine atom here, chlorine atom here, chlorine atom here, and then draw a single bond here, single bond here, single bond here, single bond here. Now there are 4 single bonds are drawn, that is 4 into 2, 4 single bonds equal to, okay, 4 into 2, that is equal to 8 electrons. Now 8 electrons are consumed. Then you subtract 8 electron from the total number of electrons. 26 minus 8 equal to 18 electrons. There are now 18 electrons remaining, which can be distributed around this terminal atoms, which can be distributed as pairs. Now you cannot, there is a hydrogen atom there, it cannot be added, pair of electron cannot be added. For hydrogen it is only a duet electrons, duet of electrons are required. So you cannot add pair of electron to the hydrogen atom, electrons should be added as pairs to the remaining atoms. So let us add here, 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 here. So now I added 3 lone pairs around this chlorine atom. So 3 lone pairs means 6 electrons. There is a single bond, there is a single bond here, there is, that means 2 electrons. So now number of electron around this chlorine atom is 8. Similarly you distribute here pair as lone pairs, again the number of electrons around the chlorine atom is 8. Here is 8, here is 8, here is 8. Now we distributed 18 electrons as pairs to that. We have 6 plus 6 plus 6. There are 3 lone pairs, 3 lone pairs, 3 lone pairs. So the each the 3 lone, okay, 3 lone pairs means 3 into 2 6, 3 into 2 3 into 2 6, 6 plus 6 plus 6 18. So now the count the number of valence electrons, it should be 26. Here is a 2 electrons, here is a 2 electrons, here is a 2 electron, here is a 2 electrons. So 8 electrons, 8, okay. So there are 4 single bonds, and then there are 1, 2, 3, 4, 5, 6, 7, 8, 9 lone pairs, okay. So 4 into, that means 4 into 2 equal to 8, so 9 into 2 equal to 8, so 18. So in total there are 26 electrons. So the number is matching with the number of electron counted at the beginning. Now you have to see whether the central atom, this is a carbon is a central atom, whether it attains the octet rule of electrons or not. Now it attains 8 number of electron, it has 8 number of electron, because there is a 2 electron, there is a 2 electron, there is a 2 electron, there is a 2 electron. So 2 plus 2 plus 2 plus 2, 8 electron. If you look at this chlorine atom, the number of electrons is 8, because there is a 2 electron, 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 8. Similarly for other 2 atoms. For hydrogen it is only 2 electrons. So now now we made sure that the octet around the central atom is right. So that means the structure is done. So the drawing Lewis dot structure is done. Let us see in another example, CH2O. Now number of valence electron is the first step, determining the valence electron is first. So carbon plus 2 hydrogen atom plus O. Carbon has 4 valence electron plus 2 into 1, hydrogen has valence electron 1 plus oxygen atom has valence electron 6. So that is equal to 4, 6 plus 12. There are 12 valence electrons available for CH2O. The central atom is the carbon, and arrange the remaining atoms like this. Now 3 single bonds are formed. 3 single bonds means 3 into 2, 6. So 12 minus 6 equal to 6 electrons. That 6 electrons should be distributed around the atom such way that each atom contains 8 electrons. That is 6 here, if you put here and if you put here, now 6 electrons are added to the oxygen atom and it attains, this oxygen atom attains 8 electrons. But if you look at the number of electrons around this carbon atom, it is not 8, it is only 6. 2 electron, 2 electron, 2 electron, it is 6 only. Then what to do? You have to take away the lone pair of electron from the oxygen atom towards carbon atom, then it gives carbon O like this. So, basically we converted a lone pair of electron to a bonding, bonding electron. Now, if you count the number of electron around the carbon atom is 8, 2 electron, 2 electron, 2 electron, 2 electron, so 8. So, 8 electron. Around oxygen atom 2 electron, 2 electron, 2 electron, 2 electron, 8. So, the octet is obeyed. The octet rule is obeyed. The molecule is very stable. This is how one has to draw the Lewis dot structure. Thank you.